Welcome back to another installment of our journey through the captivating world of functional analysis. If you are just joining us, a warm welcome to you. Don't forget to subscribe to our channel to ensure you don't miss out on any of the exciting mathematical insights we are exploring together. For those who have been following along, I do and strongly appreciate your continued support and enthusiasm for delving deeper into the intricate world of mathematics with me. In our previous episode, we embarked on an exploration of compact operators, right? Uncovering how they provide us with a lens to capture essential characteristics within complex mathematical spaces, much like a camera with limited zoom capturing key elements of a vast landscape. Now, building upon that understanding, we are about to dive into the enthralling territory of the Riesz-Fredholm Theory. The Riesz-Fredholm Theory actually serves as an illuminating extension of our knowledge of compact operators, allowing us to delve even further, right, into the fascinating interplay between linear operators and the underlying structures they operate on. So, just as each chapter in the book builds upon the preceding one, our discussion today will add layers of depth and comprehension to our grasp of the intricate tapestry of functional analysis. So, I invite you to fasten your seatbelt, right, and get ready to unravel the captivating intricacies of the Riesz-Fredholm theory. So, we start with some useful preliminary results, right? So, this would be the Riesz Lemma, so lemma 6.1, I think so. Yep. So, oops. Lemma 6.1. So, this is the Riesz Lemma. So, this is the Riesz Lemma. Good. I managed to fit it here. Nice. So, let E be a non-vector space. So, let E be a non-vector space. Just write NVS for non-vector space. And let M, right, be a closed linear space. Such that M is different from the whole space E. Then put it in column. This is the conclusion. For every epsilon positive, there exists U in E, right, with norm 1, such that the distance of U to M is actually greater or equal than 1 minus epsilon. So first of all, what you have to notice is that from this conclusion you can already see that epsilon should be strictly less than 1, right? Otherwise, this is totally obvious, like there's nothing to show. And let me just highlight some key properties of the set M. So M should be a closed linear space, right? By linear space here, I mean vector space, right? This is totally different from linear space that you probably know in incident geometry. Okay, so let's go into the proof. So proof. So for the proof, proof is quite easy but constructive as well. Let V be an element of E, right, such that V is not in M, right? So you should note that such a V, right, exist since M is different from E, right? And E is a non-vector space, so it's totally means it's non-empty, right? So okay, now since V is not an element of M, right? And that M is closed, then the distance of V to M, right, that we denote by Z, right, is actually strictly greater than 0. Now, by characterization, of the infimum, there exists M0, let's call it M0, right, in M such that G is less or equal than the norm of V minus M0, right, which is less or equal than G over, this is not right, G over 1 minus epsilon, right, and this is of course for every epsilon positive, and then as I said, 1 minus epsilon is actually, well, let me just write it. I mean, not that G over 1 minus epsilon is actually strictly greater than G, right, since 1 minus epsilon is strictly between 0 and 1. Okay, so we have this, right? This basically follows by characterization of the infimum, right? Because the distance of V to M is actually the infimum of the norm of V minus M, right, M in capital M. Okay, so then if you set U to be V minus M0, then we normalize, right, for the norm of V minus M0, right? So this U actually satisfies, then U satisfies the required properties, right? So I mean, we can already see that the norm of U is 1, right? Now probably what we need to show now is that the distance of U to M is greater or equal than 1 minus epsilon. So indeed, for every M, capital M, right, you have the norm of U minus M, right, is equal to the norm of V minus M0. I'm just replacing U by its value. So this is this minus this, right? And now, well, just expanding the difference. So this will be the norm of V minus M0 plus M times the norm of V minus M0, right? The whole thing divided by the norm of V minus M0. Now, and of course, this is actually greater or equal than G over the norm of V minus M0, right? Which is, of course, greater or equal than 1 minus epsilon, right? So, where does this inequality comes from? Well, observe that M0 plus M times the norm of V minus M0, oops, right, this is an element of M, right, because M is actually a linear space, I mean it's a vector space. Right, so this is the end of the proof. Good. Okay, well, let me just comment a bit this lemma once again. So the Riesz lemma basically says that within the norm vector space E, right, one can always find a vector that is almost as far away as possible from M, while still being restricted to the unit sphere. So this is basically what the theorem says. And you even see that, I mean, as a remark, right, that if M is finite dimensional, right, I mean, if so if this space M here is finite dimensional, right, or marginally if M is reflexive, right, one can choose even this epsilon to be 0, right. So this sense is even kind of, you can make this distance even I mean big enough further. So let's have a remark, the remark that I just mentioned. So remark, if this M is finite dimensional, it's finite dimensional, right? Means M is finite dimensional, then it is automatically reflexive, right? But or marginally if M is reflexive, but this is even weaker, right? This is a weaker assumption even. So if M is reflexive marginally, so finite dimensional. One can choose, let me just write it down here. One can choose epsilon to be 0, right, in the Riesz Lemma above, right? So let me just highlight. Okay, so now let's move on to the Riesz theorem itself, right? Theorem 6.5. Yeah. It's actually very important to have notations, numberings of theorems and propositions, right? As it is actually easy to refer to when it is needed. Okay, so the Riesz theorem says that let E be once again a norm vector space, right? With probably put it in color. With the closed unit ball being compact, in E being compact. So the Riesz theorem says that if the closed unit ball in E is compact, then E is finite dimensional. Looks agree? Finite dimensional. Okay, so proof. Well, the proof is, I mean, you proceed by contradiction. So we assume that the closed unit ball in A is compact, right? But A is infinite dimensional, right? That is A is infinite dimensional. So what we will do is that we are going to construct a sequence, right, of element of the closed unit ball in E, right, that does not have a a convergent subsequence. And this will be a contradiction because the closed interval is actually assumed to be compact. So this is basically the main idea of this proof. Okay, so we start by choosing. So we choose u1. We choose any, right? Because we choose any u1 in E, right, with norm of u1 equals 1, right? Now, this is possible, because, E is infinite dimensional. So now put E1 to be the vector space spanned by U1, right? So this is basically the span of U1, right? So, oops, E1 is obviously a one-dimensional proper subspace of A, right? One-dimensional proper subspace of E, right? Because A is infinite dimensional, so, and it is also closed, right? Because finite dimensional linear subspace is closed of E, the one-dimensional proper subspace of E, and is closed. So by the Riesz lemma, right, that we just prove. So by Riesz lemma, we can find, there is let's say u2, right, in E, right, with norm 1, such that the distance of u2 to the set E1, right, is actually greater or equal than 1 over 2, right? So I just use epsilon to be 1 over 2, right, in the Riesz lemma. So this means, oops, put it up here. So this means that the norm of u2 minus u1, right, is greater or equal than 1 over 2, right? Because this norm is actually greater than the distance of u2 to e1, right? Because u1 is an element of e1. So this inequality also holds. So now the element u1, u2 generate the two-dimensional proper closed subspace that we call E2, right, of E. Right, so what we mean is that we put E2 to be the span of U1, U2, right, and again by the Riesz lemma, there is some U3 in E, right, with norm 1, right, such that the norm of U2, of U3 minus U, right, is greater or equal than 1 over 2. And this holds, of course, for every U in E2, right? So in particular, this is true because, the Riesz lemma says that this distance to E2 is actually greater or equal than 1 over 2, right? So, and then I apply the Riesz Lemma with epsilon equal 1/2 again. So in particular, you have this, norm of u3 minus u2 minus u1 first, greater equal than 1/2, and also the norm of u3 minus u2, because u1 and u2 are element of E2, so these two inequalities hold. So proceeding by induction or iteratively, if you want, we obtain the sequence, let's say En, right, of finite dimensional sequence of finite dimensional finite dimensional subspaces of E, such that the sequence is even increasing, so that En minus 1 is contained into En, right? And of course En minus 1 is different from, or let me just write it and just use the short notation. Okay, this is strictly contained into En. Good. We also obtain the sequence, right? We also obtain the sequence UN with UN sorry, with UN in En, right, such that the norm of UN equals 1 and the distance of UN to say En minus 1, right, is greater equal than 1/2, right? So observe that this implies that this is a sequence of element of the closed unit ball, right? Okay, so in particular, you have that the norm of UN minus UM, right, is actually greater equal than 1/2, right, for provided that M is strictly less than N, right? This comes from these conditions, basically, right? Okay, because if M is actually strictly less than, if M is strictly less than N, then you agree with me that EM is actually simply contained into, it's contained, right, can be also be equal to En minus 1, right? And so this means UM is an element of En minus 1. Okay, so we get this, right? So, and obviously, right, because we see that the norm of UN minus UM is greater or equal than 1/2, so obviously UN, right, cannot have a convergent subsequence, right, which contradict the assumption that which contradict the assumption that the closed unit wall is compact. Right, so with this we end the proof. Okay, so our next theorem, right, will be before we wrap up, so our next theorem, so this will be theorem 616. Oops. Doesn't look straight. Good. So our next theorem is, will be the Fredholm alternative. Right, so, well, as I said before we wrap up, I just want to tease you with the incredible Fredholm alternative theorem, right? So this theorem actually addresses the solvability of integral equations, right? Providing conditions under which solutions exist and are unique even. So if you are as excited as I am to learn more about Fredholm alternative, right, then you won't want to miss out on my next video, right? So make sure you subscribe to stay updated and see you in the next video. So I'll just write here to be continued. So see you.